large deviation theory. We discussed earlier about laws of large number, then central limit theorem. So we will consider the same sequence of random variable again. Suppose xn is a sequence of IID random variables, each with common mean mu, and Sn is summation of xi's as defined earlier. Now we know laws of large number and central limit theorem. They are concerned with the behavior of Sn for large n. Now this large deviation theory deals with the tail probability of the form probability Sn by n greater than equal to a. Suppose Sn by n, if I consider, suppose if it is a continuous case, suppose this is some Sn by n and this is suppose f of Sn by n, the PDF, we are considering the PDF, maybe this is some distribution like this. So we are concerned with the tail probability. Suppose this is a point A, so what is the probability that Sn by n is away from A. So Sn by probability that Sn by n is greater than equal to A. So such probabilities are known as tail probabilities, and they are very important, for example, to determine the error or probability of some rare event, etc. Now let us go back to laws of large number and CLT, how they can deal with deviation from the mean. As the name large deviation implies, we have to deal with large deviation from the mean. Suppose Sn by n, that is the sample mean, and according to weak law of large number, it converges in probability to mu. What does it mean? That the probability that Sn by n will deviate from mu by a very small amount, epsilon, that probability is 0. As n tends to infinity, that probability will become 0. Therefore, weak law of large number does not allow any deviation from the mean, does not allow deviation from the mean. So any tail probability will be automatically 0 here. Now let us consider CLT. According to central limit theorem, this is CLT. Sn minus n mu, that is the deviation, divided by root n sigma, that is standardization. In distribution, it converges to normal 0 and normal distribution with mean 0 and variance 1. So because of this, now we can determine the probabilities of this form only, because it is normal distribution. I know that normal distribution is a, suppose if it is a 0 mean normal distribution. So this distribution, standard normal distribution, this is suppose z, fz of z. Now it is a short tail distribution as normal distribution is, and therefore we can find out the probability of this form only, mu minus a by root n, mu plus a by root n. So that way, because as n goes to infinity, this term will become smaller and smaller. Therefore, it cannot deal with, we can find probability deviation of the order of 1 by n. Okay. So that way we can find out probability of this form, and this deviation is very small. It cannot deal with, if there are large deviation, Sn by n takes some large deviation, this type of probability cannot deal with. That is the limitation of central limit theorem. Thus, CLT is not applicable for finding the probability of the large deviation from the mean. from the mean. Okay. So we see that weak law of large numbers does not allow any deviation, but central limit theorem allows deviation but not very large deviation. These deviations are known as normal deviations. So now large deviation theory can deal with the probability of large deviation. So it basically exploits the moment generating functions to find out these probabilities. That is, we want to find out the probability that Sn by n is greater than equal to a. So we want to find out tail probability of this form, and it exploits large deviation theory exploits the moment generating function MGF for a random variable x. We know this is mx of x is equal to e of e expected value of e to the power sx. So this MGF is used to derive these probabilities. Okay, let us see. First we will go to Chernoff bound. One very important result, Chernoff bound, that is probability that x is greater than equal to a. Suppose x is a random variable, how to get the probability that x greater than equal to a. So we have various inequalities like Chebyshev inequality, Markov inequality, etc. Here also we can apply the Markov inequality to find out this Chernoff bound. You can consider like this. Suppose we have to find out probability that x is greater than equal to a. Now we will take the exponential of both sides. So this is same as probability that e to the power sx is greater than equal to e to the power sa. We are first taking the exponential with respect to s. S is a positive, s greater than 0. So this we can write from here, because x is greater than equal to a. Now we are taking the exponential with respect to a positive number. So e to the power sx will be greater than e to the power sa. Now apply the Markov inequality. So this will be less than equal to e of, this is a positive quantity, e to the power sx divided by e to the power sa, that we can write as e to the power minus sa. So this probability will be always less than equal to this. This is for s greater than 0, and this quantity is nothing but so this I can write as e to the power minus as into mx of s. But this quantity is less than equal to this, and where s is greater than 0. So if it is less than equal to this quantity for all s greater than 0, out of that there will be one minimum. Suppose for all possible s, we consider the one which has the minimum of this expression, then we will have probability of s greater than a will be less than that minimum also. Therefore we ultimately we can write that this is less than equal to minimum s greater than 0 e to the power minus as into mx of s. So this is the Chernoff bound. So it is one of the tightest bounds. For probability of x being greater than equal to a is bounded by this. So lower bound is, this is the lower bound, sorry, this is the upper bound. So this probability cannot exceed that. So, we will be using this Sarnoff bound to find out the probability, tail probability for Sn by n. We will state one important theorem, that is known as the Cramer's theorem. That theorem is the most fundamental results of large deviation theory that we will be discussing now. We are considering a sequence of IID random variable, independent and identically distributed random variable with constant mean mu, and the MGF mx of s, which is finite in the neighborhood of s is equal to 0. So, that is one important assumption, that in the neighborhood of s is equal to 0, mx of s is finite. So, we are considering a particular sequence of IID random variables. Then for a greater than mu, this a is greater than mu, that is the mean of xi is mu. So, we are considering a number a greater than mu. So, for that the probability, log of probability, this is log is base with respect to base e, log of probability of Sn by a. So, we are considering this limit n tends to infinity 1 by n log of p of Sn by n greater than equal to a. So, this term we are considering, this is log of probability, then we are dividing by n, that is, that limit is equal to minus L of a. So, what is L of a? Now, this L of a is related with this moment generating function. So, this is equal to L of a is equal to maximum of s greater than equal to 0, s a minus log of mx of s. So, and if S star is the point of maximum, suppose L a is the expression, it is a function of a for which this S a minus log of mx of s attains the maximum value. Suppose S star is the point of maximum, then L a we can write it is S star a, because s is S star now, log of minus log of mx of S star. So, this is the rate function, this function is called rate function. Why it is called rate function? Because it will determine the probability. Now, it is a probability rate function. How it can determine the probability? Suppose this expression is there, if I multiply by n, then it will be L a into n. Therefore, and if we log is given, so if we take the inverse log, then probability of Sn by n greater than equal to a will be approximately equal to e to the power minus n into rate function. So, this is the tail probability. Now, we can determine, because this is a as n tends to infinity, therefore, for large n we can approximate this probability by this result, that is probability that Sn by n is greater than equal to a, that is approximately equal to e to the power minus, there is a rate function L a is there, that is the rate function multiplied by n. So, this is the probability. What is L a now? L a is related with the log of the moment generating function, log of MGF. This is also known as cumulant generating function. So, the difference between SA and log of mx of s. So, this is a line, this is another function. So, what is the maximum difference between them? So, that is LA, and it will determine the tail probability. This is what Cramer's theorem says. Now, this probability that Sn by n is greater than equal to a, Cramer's theorem says what is the value of this probability as n tends to infinity. So, first of all we will find out what is the upper bound for this probability. So, for this we can apply the Sarnoff bound. So, probability of Sn by n greater than a This is same as probability that Sn is greater than Na. So if I apply the Chernoff bound, what we can write? That is less than equal to minimum over S greater than 0 of e to the power a n s, because here now right hand side is Na, so we are writing Na here, into m, this is the random variable, m s n of s. This is because we know that probability of x greater than equal to a, here we are writing greater than, doesn't matter, then here it will be less than equal to minimum over s greater than 0 of what? E to the power a s into mx of s. That was the Chernoff bound that we have used here. So here constant random variable is Sn, and then it is greater than Na. Now since xi's are IID, so m Sn of s, this is by definition e of e to the power s into Sn. So that is equal to, now we can write this as equal to e of e to the power s into summation xi, I is equal to 1 to n. Now this we can write as a product because it is exponential, so that way we can write e of product of I is equal to 1 to n e to the power s xi. And now we know that xi's are independent random variables, therefore e of s xi is that exponential of these independent random variables, they will be also independent. So because of that, this e I can take inside, so this will be product of I is equal to 1 to n e of e to the power s xi. So this is nothing but moment generating function m of xi. So this is nothing but m xi of s. Since IID, each of the random variable will have the same moment generating function, therefore this I can write as m Sn of s is equal to moment generating function of x to the power n. So this is the moment generating function of Sn of the sum when xi's are independent and identically distributed. And therefore what we can write now, probability of Sn by n greater than a, that is less than equal to minimum over s greater than 0 e to the power a n s, because Sn will be greater than equal to Na, into now moment generating function of Sn is equal to mx of s to the power n. So we can write like this. So now we have to find out the minimum of this quantity. If I write this also in terms of exponential, then I can write as ans plus n log mx of s. So this minimum, suppose this is now minimum of this expression will be obtained when this expression is maximum. Okay. So if I consider, suppose this minimum of the entire exponential expression, so the exponent whenever it is maximum, that the expression will be also maximum. So that way we have to maximize the exponent part. So if that is the maximum is n into La, then we can write that this probability that Sn by n is greater than a is bounded by, it is less than equal to e to the power minus n into La. What is La here? Where La is maximum s greater than 0 Sa minus log of mx of s. So if s star is the maximum point, then we can write it La is equal to s star a minus log of mx of s star. Therefore, we have shown that that probability that Sn by n is greater than a, this is bounded by e to the power minus n into L of a, where L a is given by this. So, this is a consequence of Sarnoff inequality only. Now, how do I find S star? S star is the point where this expression S a minus log of mx of s is maximum. Therefore, if I take the derivative with respect to s, that should be at s is equal to s star, that should be equal to 0. So, if I take the derivative with respect to s, this will become a, this will become 1 by mx of s into mx dash of s. So, from that equating to 0, we will get a equal to mx dash of s star divided by mx of s star. So, now this a is related to the MGF by this relationship. A is equal to mx of s star divided mx dash of s star, differentiation of mx of s at s star divided by value of mx of s at s star. So, therefore, what we get then, probability that Sn by n greater than a is less than equal to e to the power minus n into La, or if I take the logarithm, I take the logarithm first, then it will be minus n into La will come. So, that n, if I keep at the denominator left hand side, we will get this 1 by n log of probability Sn by n greater than a, that will be always bounded by minus La, where La is the rate function given by this relationship. Okay. So, that way we are able to find out an upper bound for this probability, tail probability upper bound is given by this relationship. But we have found out the upper bound. So, that is 1 by n log of base E, probability that Sn by n is greater than a, that is bounded by. So, we want to show that for large, this is the upper bound only, we have to find the lower bound also for this expression, so that we can find out the limiting case. So, we have to show that for large n, limit as n tends to infinity 1 by n log of probability that Sn by n is greater than a. So, this will be greater than some lower bound, that is again given by La plus epsilon, where epsilon is arbitrarily small, So, this result we have to establish. This is a slightly complicated task. So, so far we know that this the probability, the logarithm of the tail probability is related to the rate function, but we have a upper bound for this expression which is bounded by the rate function. Next, we will show that this quantity as n tends to infinity, it will be greater than minus La plus epsilon. So, that in the limiting case we will get both lower bound and upper bound. If we consider, then this will be equal to minus of La, that we will establish.